Welcome to the Foundry by Forge College. I'm absolutely thrilled to have you here for today's explainer. If you're following along in our applied Solidity development track, well, you know that in our last session, we were deep in the trenches with debugging labs and troubleshooting techniques. Yeah, we spent a lot of time crying over broken code, didn't we? Well, today, we are officially shaking off the trauma of those debugging sessions and getting back to building. Specifically, we're drafting the blueprint for an ultra-secure, highly optimized, automated bank vault on the blockchain. This is a massive milestone in our module on integrating Ether with complex state management, which sits right inside the Ether and advanced state management section. We are finally bringing together real money and on-chain data. So, here's our master schematic for the day. First, we'll look at mixing money and state safely. Then we'll dive into the deposit blueprint, followed by the pull withdrawal vault. After that, we'll hit checks, effects, and interactions, run through some testing and gas inspections, and finally, get you ready for the capstone.
All right, Section 1, Mixing Money and State Safely. Let's start the site survey for our new smart contract architecture.
Okay, so how do we mix Ether and state without causing a total catastrophe? Listen, mixing live Ether with your contract's internal state is exactly like running water plumbing and high-voltage electrical lines through the exact same wall. I mean, if you don't do it perfectly, if there's even a tiny leak, you don't just get a little puddle, you get a highly expensive explosion. When a user sends Ether to a contract, we have to record that balance in the contract's memory, right? Its state. But every single time we touch that state, it costs us computational fuel or gas. So the big question is, how do we securely link the flow of money to the updating of data without bankrupting our users with crazy transaction fees? Well, the biggest culprit for high gas costs is an operation called SSTORE. To keep our automated vault efficient, we absolutely have to avoid unnecessary SSTORE operations. Think of SSTORE as a massive tax on your contract's electricity bill, or, a hefty extra baggage fee at the airport. Every time you save a new piece of data to the blockchain, boom, you pay this fee. And if you save data inefficiently, you pay it multiple times. So our goal today is to pack our bags so perfectly efficiently that the network barely even notices we're there, even as we handle complex Ether transactions. Moving on to Section 2, the deposit blueprint. Let's zoom right in on the deposit chute of our blueprint. Now take a look at how we've engineered our data structure here. This table outlines our account struct, which is essentially a custom data container. Instead of using massive default data sizes, we are tightly packing specific variables. We're using a uint 128 to track the balance, a uint 64 for an epoch state counter, and a simple boolean just to mark the account as active. Because these smaller data types add up to less than 256 bits, the Ethereum virtual machine can literally pack them all into a single storage slot. By packing our storage suitcase perfectly like this, we completely dodge those expensive SSTORE baggage fees we just talked about. It's just a really elegant, highly optimized piece of engineering. So the crucial point is how we actually write the code to use that pack structure. We intentionally separate our public-facing deposit chute from the internal ledger updates. The public deposit function simply catches the Ether and makes sure the user actually sent something, meaning the value is greater than 0. Then it passes the job to an internal helper called apply deposit. This internal helper handles the delicate state updates. And look at that last bullet point. We use an unchecked block for incrementing our epoch counter. Because we know mathematically it won't realistically overflow in our specific use case, we can tell the compiler to just skip the safety math checks. This brilliantly bypasses redundant background operations and saves us even more gas. All right, Section 3, the pull withdrawal vault. With funds safely inside and our data elegantly packed, we need a secure way to let users take their money out when they want it. Let's see how this builds our security model. In the early days of Web3, developers used to push payments. That means the contract would automatically send Ether to users when certain conditions were met. Honestly, this is a terrible idea. If the receiving user is actually a malicious smart contract that intentionally rejects the incoming funds, it can cause a revert that breaks your entire system. We never want to force-feed money back to users. Instead, we use the pull payment pattern. We build a secure, isolated vault where the user must explicitly step up and request their own withdrawal. It shifts the risk of failure away from our contract and entirely onto the user making the request. Which brings us to Section 4, Checks, Effects, and Interactions. To make sure our pull withdrawal vault is completely impenetrable, we rely on the ultimate safety checklist. And this brilliantly illustrates the absolute golden rule of Solidity. checks, effects, interactions. This is the holy trinity of security. Step 1, check. We verify the user actually has enough money in their balance. Step 2, effect. We deduct that money from their internal account screen, which is our state. Step 3, interaction. Only after the state is completely updated do we actually send the physical ether out to them. Think about it for a second. A bank teller would never ever hand you a stack of cash before deducting it from your account screen, right? If they did, you could theoretically ask for the cash again before they updated the computer. You must rigidly follow this 1, 2, 3 mechanical process to prevent catastrophic re-entrancy hacks.
But wait, what if step 3, actually sending the ether, fails for some reason? Maybe the network is super congested or the receiving address has some weird issue. If the transfer fails, haven't we already deducted their balance in step 2? Well, don't panic. By wrapping our transfer in a requires sent statement, we create a brilliant little safeguard. If the interaction fails, this line guarantees that the entire transaction reverts, and our internal ledger instantly reverses the deduction. The user's balance is magically restored as if the attempt never even happened. It's just a perfect fail-safe mechanism. Now for Section 5, testing and gas inspections. Every good architect requires a rigorous stress test before signing off on the blueprints, and hey, we're no exception.
You see, testing isn't just about making sure the money goes to the right place. It's about checking the efficiency of our plumbing. This introduces the concept of gas regression. Gas regression means measuring the new computational cost of our contract and comparing it to our older, simpler versions. As you dive deeper into the courses and community programs at Forge College, you're going to learn that preserving gas optimizations is an ongoing battle. We want to confirm that adding these new ether flows hasn't completely ruined the beautiful state optimizations we built earlier. So, what exactly is our benchmark for success here? Well, our strict engineering tolerance for this module dictates that adding these complex ether flows to our previously optimized state updates should increase the combined gas cost by no more than 15%. That's the magic number. If your test runner shows a gas spike of 30 or 40%, it means you've introduced redundant writes or inefficient logic, and you need to march right back to the drawing board to tighten up your code.
Beyond just gas, we must perform negative testing. Guys, it is not enough to prove that the vault works when people politely follow the rules. We absolutely must try to break our own vault. We simulate bad inputs, like someone trying to deposit 0 ether just to bloat our state data. We simulate greedy users trying to perform double withdrawals, trying to trick our checks effects interactions pattern. If our negative tests pass, it proves our defensive checks actually work out there in the wild.
Finally, Section 6, ready for the capstone. Let's finalize our blueprints for the next major phase of construction.
Just look at what we've accomplished in this explainer. By keeping our external surface minimal, literally just a clean deposit and withdraw function, and by keeping our internal data rights highly concentrated and packed, we have successfully preserved our gas savings. We've heavily tested both the happy paths and the attack vectors. What we have created today is a perfectly modular, highly optimized vault component that is completely ready to plug directly into a larger architecture.
So, as we wrap up this blueprint, I want to challenge you to think about the bigger picture. How will this vault module interact with other components at a massive scale? That is exactly what you'll be tackling in your capstone project. To master this architecture, dive into the code, and explore other fascinating Web3 topics, I highly encourage you to visit forge.college. Grab your tools, keep practicing those integrated patterns, and I will see you in the next explainer.